Yeah, I just cut and pasted out of Whitworth's book, I think. I don't remember. But I did the thing and he had the answers.
Cool.
The biggest problem is people get in a hurry and you almost reacting like, oh, it's always wavelengths towards generator, not wavelengths towards load, stuff like that. Okay, so for today, I want to go through stub tuning, but matching, but now we're going to use transmission lines. Y'all hear me on this class? We're going to replace the elements with transmission lines that will have the exact same reactive value, normalized reactive value, either plus or minus. So the best way to show you this is I'll go through a problem. The way I want to do this is go through a problem in your book that you've done with the reactive element. Then we're going to show you how to do it with transmission lines. Now, a transmission line can either be a short or an open. So for that one, I gave you some reading, right? I asked you to try some problems, didn't I? Or not?
No, I did not see it.
It was there?
Yeah, it was there.
Yeah, it was there.
Mm-hmm.
Oh, I didn't see it.
Well,
There's a lot.
did you have any question about that?
Where is it? Is it on like
One now?
It's on OneNote.
It
is it
should
under
be
homework 4 or the quiz solutions?
Should be homework for
It's homework 4.
Yeah, that was
It's just the YouTube videos and this thing. 2, 3, 3, 5, 3, 6, and some YouTube videos.
I did those problems. I just didn't. Is there?
Let's go ahead and here's what we're going to do. We'll do problem 2.35 first with an element. Then we're going to do it with transmission lines, okay? So we'll set this up. So for this problem, if you can, if you've got a book, you can tell me this is problem 235, and you'll see what I'm talking about when I do it. 235. I'm going to get my yield Smith chart here. You can take one out, and it's smart to do that. Stay up to date with this stuff. This is the problem, but we're going to do it using a transmission line, either in series or shunt, with that will have the same effect. It'll actually repeats match it. So for this one, can you give me the
Imagine that we're using a reactive element in series with the length D of T line.
Yeah, isn't it? Is this the one? Doesn't it have a reactance? Oh, we'll just do it anyway. Never mind. Go ahead.
Is to be used to match a 35 minus J50 ohm load to
So 35 minus J50 and the load, Z0 is?
100 ohms
This is going to be a little tough. Go ahead.
at 1 gigahertz.
Okay, 1 gigahertz. And what do they want now?
And then find the through line length D and the value of the reactive element if A, a series capacitor is used, and B, a series inductor is used.
Okay, we're going to do it. And this, again, is basically what we've been talking about before, right? But then we're going to use a transmission line. I want you to be attentive here. So first of all, when we do this, what's the first step? Always, if we've got matched,
Normalize.
yeah, we've got to get ZL. If it's a load's given and we're matching it, and that's going to be 35 divided by 35 minus J50 divided by 100, or 0.35 minus J 0.5. So if you've got a Smith chart and you look for that thing, 0.35 is a circle. It's about here. If you look on it, there it's 0.35 is the real part, and minus J 0.5 is down here. Now this is minus J1. Minus J 0.5 is about here, so the trajectory will come here. It's about here should be your ZL, and that would be 0.1. Y'all follow me, class? We did this one, didn't we?
Yeah, we've done this one.
All right, we're going to go through it again, and we're going to do it with transmission lines replacing this stuff, okay? So first of all, when I come down here, I have to take a line, and I have to go right from here through ZL and shoot it out, and then I need a mile marker, wavelengths towards generator right here. Can you just do that to me? And you can tell me from before.
0.4196 lambda. That's what I got.
So this is 0.4196 lambda right here. And I'm just showing you that. Now you need to take your compass and just make a circle of constant impedance like so, or constant deflection coefficient. Here, just take your time and do it. You know what I'm up to, right? We've done this several times. And if you do that, you got a good compass now. Smart move. It'll help you. Anyway, take it down here. But you're going to hit 2 points. These are the 2 points. These are conjugate points. This is going to be 1 plus j something, and this is 1 minus j
It's
something.
1.4.
What is it?
1.4.
1 plus j 1.4, and this is 1 minus j 1.4. Right? About. Do you all agree with that, class? Now, next thing you're going to do is shoot a line through both of them, both these points from center, and give me the wavelengths towards generator there. We're going to need them both.
That's 0.1738.
So 0.1738,
The other one's 0.327.
0.327 wavelengths towards generator. Now, in this, does he say it's in series or parallel? I think it says series.
I'm not sure.
Series
Series capacitor
Series.
and series inductor.
All right, remember, we can put it in shunt, then we have to do it in the admittance domain. You all remember that?
Yeah.
Series, these are going to be series elements. Now, think about this. Next thing I want you to take note of. When we're here and we move to here, the reactance, normalized reactance is 1 plus J something, right? So to get rid of that reactance, the reactive impedance right there, we have to add a negative J impedance, right? You all with me? What has a negative J impedance? Capacitor, right? So we're going to add a capacitor. Does everybody follow me on the reasoning class? All right, so now I've got to say that this value, J 1.4, I'm going to have to get rid of, so I want minus J 1.4. Remember, that's a normalized impedance. Everybody? So I'm going to set that equal. This, if we go from here to here, we're going to put capacitor in series. And the capacitor reactance is minus J over omega C. Does everybody agree with that? Or 1 over J omega C. You all with me, class?
Wait, so why did we do the minus J1.4? Because it's capacitor.
That's right. We are saying we need a capacitor. This is a positive J. We need to add in series with it a minus J.
Okay.
All right, now that's not normalized yet, right?
Yeah.
So to normalize, I have to divide this by Z naught. Everybody follow me on this? Y'all, are you with me on this one? Now, if you look on this, what happens? The J's go away, so now I have C is equal to 1 over 1.4. I'll get out of your way in a second. And it's going to be times Z naught, and then it's times omega, and omega is 2 pi f. I'm going to move out of the way, but I want to make sure you all see what I'm doing. Make sure you grasp it. And don't be casual like, oh, I got this. Make sure you see all aspects of it. Y'all with me, class? All right, now for that one, we might as well get this. We did it last time. We have 1 over 1.4. Then Z naught is 100, you said, right? 100. And then we have 2 pi, and that's a gigahertz, right? So it's times 10 to the 9. And can you give me the value of that capacitor? We're going to replace that with a series transmission line.
1.14 picofarads.
You might as well get the distance. We did. What would D through for this one be? If this is a capacitor model. We just calculated the C over there is 1.14 picofarad, correct, class?
Yeah.
Everybody see this on your Smith chart? How to do it? Class, are you with me? All right, now, next, what's the D through going to be? This is an important point. I want to make sure you see this. I ended up at this mile mark, right? So that's where I start from. I go to the mile marker I ended up at minus the mile marker I came from, and then I add 0.5 if it's negative. So if you look at this, it's going to be 0.1738, right? And I subtract from it 0.41 or 1 was it 1 or 41 what?
41966.
916. Read my own. It's negative, so I have to add 0.5, and that would be the value in wavelengths. Can you give that to me? We get this problem.
I got 0.2542.
Is that about right?
Yeah.
And here's how you can tell about that's right. All right, if you went right across to here, it would be exactly a quarter wavelength if I stopped there. You all with me? Every time you go all the way around, it's halfway. So if we move a little bit, yeah, it should be 0.25 something. Makes sense. All right, now that's the capacitor, and this would be a model that worked. We're going to replace this capacitor with a transmission line. All right, and we can have either the end shorted or we can have it open. Do y'all hear me, class? Now pay attention to this. This is where people mess up. So let me do it right here. And I'm going to show you this. So if we're going to attach this transmission line in series. So here's what's going to happen. That capacitor I'm going to remove. The attachment point is going to be the same, by the way, the same distance. And now we're going to have, and this is going to be a shorted transmission line like this. We're going to calculate this length. I'll call it L stub, or the length of the stub, and it's a short. And it's in series. Y'all hear me? I want you to take a good look at this. You follow me on this, everyone? Okay. So, now, and we're assuming the stub has xenon characteristic. Now, I know I want this stub to nullify this, okay? And it's shorted. It's going to be in the impedance domain. Please just take a moment, get this down. I want you to watch what I'm doing and why I'm doing it. This is going to be with a short circuit stub.
So that only the length of the top is the transmission line? Everything else is just a wire?
This is the length from here to here is D through. It's the same. It will be the same. All right, now this length is of the stub we're going to figure out. It's a transmission line, but it's shorted at the end. Y'all hear me, class? So the way I do it is this. If you have a short circuit, and this is xenon, what's the impedance of a short circuit, class? 0. It's 0, all right? Now, where is 0 on a Smith chart? Right where my finger is. So you come in right here, that's 0. Here's your actual, when you normalize 0, by the way, what do you get? Divide 0 by 0, you get 0 again. Amazing. Anyway, I'll find people that will give me a different number. It can't be that easy. The rationale sometimes I get, but how come they gave me the answer? But it couldn't be that. It's not a trick question. All right, so that's 0, right? Now, when you move, you're moving. This is the distance. You would literally put a circle on a circle. It's on the outer. Now you're going to move. How far are you going to move? Until you get minus J1.4 in the outer rim. You all hear me? So you're going to move this far. You're going to keep moving here. Don't even have to make a circle until you come down here, and somewhere about here is going to be minus J1.4. Take a look at that. Can you all find that? This is minus J1 right here, 90 degrees down. This somewhere in here is about minus J1.4. Can you all see that? All right. Can you see it in the back, by the way? Can you see it? All right. What's the mile marker there? Now take a line, draw it straight through that, out to the edge where the wavelengths towards generator, and give me that wavelengths towards generator number there. Can you see, is there something you can't see?
Oh.
No, I'm talking.
You mean?
Yeah.
Oh, I just looked down for a second. I looked up, and I don't know where we got that line. Sorry.
Which line?
The line at the bottom.
Is this, you see
the
where
central
minus
line.
J1.4 is?
Yeah.
This is on the rim.
Oh,
Go
okay,
from-
okay. We're intersecting minus J1.
Yeah, now go from the center and draw a line straight through there, right through minus J1.4, and tell me what you get wavelengths towards generator.
0.348.
0.348. You all see that?
Wait, is it just minus J1.4? There's no 1?
Yeah.
No,
that was
just
better.
there is no real part. Remember, this is this. If you got a transmission line, if you short it or open it, it can only have a reactive value.
Yeah, okay, I got it.
So you got 0 divided by 0 is 0, right there. Now you're moving, come down here, and you're going to get minus J 1.4 at a distance of 0.327 wavelengths towards generator. Can you all see that? Now, the line length is that, 0.327. It would be the length of the stub, because here it's 0. Can you all see that as the 0 point? Right? I mean, literally, it's 0 here. So we move that far, that's how long this stub is. It's 0.348, right? 348 lambda, and that's replacing this with a short circuit stub in series. Y'all hear me? Now, we're going to do the same thing, but it's going to have an open circuit stub. Y'all hear me? That means the load, by the way, I don't recommend you ever use open circuit stubs, but I'm going to cover it just because they do occasionally pop up. The reason I don't like it, you see how they're short right here? That short is probably going to be shielded in the real world. There's no plus to minus voltage that's hanging out here that could interfere with nearby circuitry. Anytime you have a voltage difference at the end, like this dangling like that, anything nearby could be affected. Yeah.
So if the open circuit is less commonly used, are we not going to see very much more in this class?
Yeah, you're going to see open circuits, but I'm just saying.
I mean with this using L stub and.
Oh yeah, we're going to do it
Okay.
both with open and short.
Okay.
All right. I'm just telling you, in the real world, it's like I told you before, you don't put inductors in parallel. Do you all remember that?
Yeah.
Why don't you? Because if you're using any DC, if it's feeding like a bipolar transistor, right? Bipolars are always have a DC offset, right? If you use that as a feed line, then you can't have DC offset. It'll short it out. So inductors, in general, for good design practices, you put inductors in series, capacitors in parallel, if at all possible. An inductor in parallel causes nothing but trouble, usually. Just telling you. Okay. So, we did this with a short circuit. Does everybody understand why we did what we did?
Yeah.
Now we're going to do the same thing with an open circuit. Let me move over here. And again, I'm just that far away. I'm going to get different values of lengths of these things to replace that capacitive reactance. So it's going to be the same distance from here. Y'all with me? All right. So here's the thing. Here's what it looks like. Still got my load here. You don't have to redraw this, but I'm going to do this just for the sake of clarity. Here's the load here. It's 35 minus J50. Characteristic impedance Z0 is still going to be 100. And now we have to find the distance away where we're going to add a stub. But this stub in series is going to have an open circuit. This is an open circuit. We're going to calculate this length. It's L stub. Everybody with me? All right. Let's go over to this drawing. And I do it the same way. What I need is, I need the normalized impedance to be minus J1.4. Can y'all follow me on this, guys? I'm going to give you a second to write it down. That's what I need to do. I've got to get minus J1.4 in series with it. It's an impedance, correct? All right, so how do I do it? This is an open. All right, if it's an open circuit, what is the impedance? The open is infinite, correct? All right, normalize it. What is it?
Infinite.
Where is infinity in the impedance domain here?
The very right.
Right here. This is infinity. So, yeah, is everybody following the rationale?
Yeah.
So at my Smith chart right here, that's the impedance. Now as I move away from there, I'm moving right on this outer rim. Y'all see this? How far do I have to go? I have to go to 0.384, right? But I have to subtract a quarter wavelength from that. Y'all follow me? Because that's where I start. It's exactly what we had before, only we subtract a quarter wavelength from it because it's an open circuit. And that will always be the case. So this stub length is going to be 0.348 minus 0.25 lambda, and that will match it too. Everybody see that? Now that's in series. Most of the time, and I don't say all the time, but most of the time, right, 99% of the time, it's in parallel. It's called a parallel shunt stub. But we're doing it in series just to make sure you understand the concept. And again, what you're doing is always nullifying that reactance. Now a question for you, just listen to me before you're ready. If we move not to this point, but to this point here, all right, now you would have to put an inductor in series. Do you all hear me on that? And the inductor would have to have a normalized impedance of plus J1.4. Yes?
Yeah.
With me, everybody? Plus J1.4. So what would the value be? It would be J omega L divided by Z naught would be 1.4 because it has to be normalized. Everybody see this, class? Are you with me on this one? Or not?
I was just thinking about it, yeah. I think it's best.
I'm saying that's what it would be for the inductor. We did this problem before, but I'm just covering my bases. Now, if we wanted to replace this point, if we move to this point and we want to use a series transmission line, then we do the same exact thing we did here, only instead of having minus or plus, we had minus J1.4 here, it would be plus J1.4. Do you all follow me? And that's the only difference if they're in series. Y'all with me on that?
Yeah.
Okay, and we could do that point if we wanted, and there are only two possibilities. Either it's a short or it's an open for a stub. Now that's in series, right? The stubs these are in series, they're not in parallel. Everybody with me? I'm going to do the parallel one. I want you to get a new Smith chart or something and pay attention to this. These things, kids, like students always confuse them. The biggest reason they do is they don't do enough problems, or they cram. The night before they try to do all the problems and they're really confused.
So we're starting with parallel short circuit.
We're going to do parallel with short and open, but you're going to see the reasoning behind it. Let me erase this. We could do this one. It almost, I think now, would benefit you to actually see a problem in the book, and you can, that has answers for what that are exactly right, so hang on.
Like, so when we did that problem, was the open circuit, was that for part B of the problem?
Yeah.
Okay.
No, it's my part.
Okay.
It's not, that's nothing to do with the book.
Oh, okay.
The book only asks for an inductor or capacitor.
Okay.
Here, we're replacing either the inductor or the capacitor with stubs.
Okay.
Either shorted or open in series. Got me, class? Y'all with me? We're missing some people. One, at least two. How many people were we missing? You got
I mean,
three?
Chase is not here, and you have another quiz, so two.
There's
Several more.
There's 2
I
people.
think I got,
I thought we had 10 people. in this quiz.
4. Yeah, there's 10.
we got one.
Yeah, 8.
One. I'm missing two people
yes.
Yeah.
that have taken the quiz. There's more that haven't come. So be it. I had one person call me up, ask me, would I be willing to do this in a hybrid format so they could take it online? I don't make those. I don't have any control. Matter of fact, I didn't even know my department head can make that. Register this group, and by the time the course begins, it's never going to change. I mean, we can go all online if there's a COVID epidemic that's astronomical, all right? But they have to do a whole bunch of stuff up there that I can't cause me to win. But I'm, no, it's not offer. Well, can you offer it? No, I can't. I have lectures you can watch online, but I can't give you any kind of a grade. I can't make up quizzes that are remote and all that other crap. But you can come here and say, no. All right. Now, we're going to do a problem, and you're going to see this. You kind of get the idea, stubs, right? Series stubs. Everybody with me? That we put them in series. Now we're going to do them in parallel. I want to tell you where this is so you can see it.
Where is this in the textbook? Is that your
This is
getting
on
right now.
page 84, shunt stub tuning. As a matter of fact, what I'll do, how do I do this? Why don't we do example 2.7, if somebody can read it to me. You got that right in front of you, right? It's on page 35, I believe. So, page 35, and this is example, what's the number on that?
It's
Page 84.
page 84.
Yeah.
Wait, why'd you say 35?
Did I read it wrong? Oh, 85. That's my eyesight.
You want to do example 2.7 or 2.8?
I said 2.7.
We can do 2.7, we can do 2.8 too, but let's do one of them for starters. It's going to be the same exact thing. Let me get my Smith chart, hang on.
85.
So here's my Smith that is, I'm not liking this marker, but I'm always strapped for markers in this class. Let me see if I got one. Just one. Well, that's kind of there. All right, let's try that one. Okay. All right, here's RQ1. And what's the problem now? They have a load, right?
Yep.
And then we got, what is Z naught for this one?
50 ohms.
And what is this load?
20 minus J 55 ohms.
And they want
A shorted.
a shorted stub in parallel.
Yes.
Usually when they say stub, now, no, I better be careful about it. They'll use shunt in parallel, and then they'll have a series.
It says shunt.
All right, so what we've got is this. We got to find the distance out here where we're connect this. And is there any limitation? Does it have to be a minimum distance from the load or minimum stub length?
That's all it says.
All right, then we'll do it my way. If I have a choice, I'll do it mine. So first we have to take this and we have to normalize. We always get ZL first. So what is ZL? That's going to be 20 minus J 55, did you say?
Yeah.
Over 50, so what's that? That's going to be
0.4 minus J 1.1.
1 point, what is that?
1.
1.1. So we're going to locate that point. Over here, if you get your Smith charts, 0.4 is a circle about this big. This is going to be 0.4 real part. Minus J 1.1 is right inside of here. This is, oh, I'm sorry, minus J 1.1 down here. So it's going to be, if this is straight down, this is minus J 1. 1.1 is about here, minus J 1.1. You can take a look. And that means the intersection of these two is right about here. And I'm just going to call that ZL, and this is my 0.1. Can you all see that? This next part's real important. We're not going to do this using impedances. We're going to use admittances. Y'all hear me? Admittances. So take two ways to do this. Take your line, go straight through the center, right through here, and where this straight line intersects the circle you drew, you should have drawn, oh, I didn't even draw the circle. I got to draw the circle. All right, so from here to here, this should be your reflection coefficient magnitude at the load. And then you need to take your compass and draw a circle. Let me do this right. We're trying to do it. So from here, you need to draw a circle that is of that radius. about like this. And you're gonna come to this point. If that's point 1, this is point 2, and it's YL, and it's simply 1 over ZL. And that's point 2, and what is the value of that? Probably just take your calculator and take 1 over that. So it's gonna have a positive value for the real part, and it's gonna have a positive value for the J part.
0.292 plus J 0.803.
803. Okay, that's point 2, right? Remember, this is admittances. Got me, everyone? Now, we're going to move, and we're going to take the shortest line from the load to the point where we can attach a stub. You all hear me? So just look, if this is point 2, we're going to move to here, this point. This is going to be point 3. And that point is going to have a real value. Remember, it's going to be y now. It'll be 1 plus j something. Can you tell me what that is?
I got about 1.9.
1 plus j, 1.9? Is that right, class? It's in this book, by the way.
Oh,
Just tell me what it is. 1 plus j, 1.9, is that right? About?
That's about, yeah.
What does he have?
He has
J2.
he has J2.
Yeah.
All right, we'll use j. I know why I chose j. It's easy. All right, with me?
Yeah.
Now take your straight edge and draw a line right from the center through that point, just straight through here. And again, we're going to get the distance we move from the load to this point where we're going to attach the shunt stub. With me, class? And how far do we move? We move from here. Oh, I didn't get this. What is this value in wavelengths towards generator?
It's about 0.15.
What is it?
Yeah, like 1.1.
1.1?
No, point
0.1. Sorry. 0.11.
5.
Yeah.
5?
Yeah.
Or like say 0.5. Like or sorry, 0.1111. 0.111.
Fantastic. All right. It's got a lot of ones in it. You with me, class? About it, right?
Yeah.
All right, now you have to get to this point. Now take your straight edge and draw it through here and tell me what you get out here for wavelengths towards generator.
0.187.
So this is 0.187 lambda. You agree, class? You follow me on this?
Yeah.
I'm making sure. What don't you follow? Just let me know. I'll help you.
Okay, why did you draw a line straight through there?
From here to here,
Yeah.
you see how this is normalized ZL?
Mm-hmm.
We're going to connect stuff in parallel or shunt. That's the admittance domain, right?
So it's just,
So we're not going to use impedances, we're going to get admittances. Admittances are 1 over
Okay.
impedances. So straight through here, this is the admittance to that point. It's called the conjugate.
You can also do 1 over Z.
What?
You can also do 1 over ZL and plot
Just take it, yeah, and you can plot that.
so then is YL just whatever is on the circle based off of,
Wait.
so ZL, so you draw your circle, one side ZL, you just go to the opposite side, that's YL, right?
Yeah, here's what you're doing. You could literally do this. Yeah, this distance is this distance from the center. You can just draw a line straight through here, take a measurement here, measurement there's YL, or you can draw with a compass a circle all the way. Where that straight line intersects the upper part, that will be YL.
Okay.
And you should get about 0.9292 plus J 0.803. I don't think that circle's drawn right.
Which circle? The
Well,
one
you
I'm
got
doing?
it.
Did I do it wrong?
Yeah, it was just
Why is this so
small.
Where did you guys go?
Can you show them where it is? Show them where the value
What's the ZL? The ZL is the,
It's
that guy.
it's
0.4
0.4 minus J1.
Oh, I just drew that completely wrong. No, that's my bad.
Do you have-
the opposite?
You good with it?
Yeah.
You guys good? This is time to help your friend. If you may help anybody that needs help, because I'm telling you, some of the stuff, sometimes you don't know what to ask. Yeah.
Oh, quick question. Are we gonna quiz this Friday?
Maybe. We'll see how at the end of this class. All right.
If so, it'd be on this, right? Repeat it.
Hopefully.
Yeah.
And pay attention.
See ya.
canceled the one in my other class in random because the material I need to cover to have the quiz meaningful, we didn't get to. But we'll get to it Friday, and I'll get one in the week, maybe on Monday or Wednesday. Anyway, you all with me on this?
Yeah.
Okay.
So the distance between there and the other point is the distance.
Yeah, from here to here.
Okay.
This is going to be the actual D value.
Okay.
So what is D going to be? It's going to be the mile marker here, which is 0.187, minus mile marker there, which is 0.11111, right?
Yeah.
That's
And that's going to be what?
0.076.
0.76 length. See in his book if he has that for the value.
it's 0.075 in the book.
It's very, very close.
Yeah.
Here's one tip. Now, I'm not going to write Wentworth a letter. Normally, a transmission line, if you cut it down and it's less than 1/10 of a wavelength, really isn't a transmission line. Just think, if you just have two pieces of wire that are super short connected to a load, they aren't a transmission line. Do y'all follow me? Normally they say you have to be at least of 1/10 of a wavelength or longer before it will act as a transmission line. You can get away with this stuff, but usually what you need to do, the way he's doing it, usually you're going to have some way of adjusting, probably putting a small capacitor in series with here where we can tune it so you get perfect match. Go ahead.
We couldn't add half a wavelength to give it because of
It's exactly what he should do
Okay.
from here. It should go this plus a half wavelength. Because remember,
Okay.
this is the one thing that's not a half wave or a quarter, less than 1/10 of a wave. You could do exactly that, and you're right. But I'm just showing you in Whitmore's book, this is what he did, I believe, right? Which is on the hairy edge of not quite working. Just telling you. Because it's less than 1/10 of a wavelength, right?
Yeah.
Okay, anyway, we're going to keep going with it. Now, here, the normalized admittance right here is this value, right? That's admittance. Now, did he say in shunt, right? Right?
Yeah.
So it's
Yeah,
admittance.
yeah.
So we're going to add a transmission line that's going to have the opposite value of J2, minus J2 as the input admittance. Y'all hear me on this? I'm going to draw it over here so you can see it. All right. So, this is my Smith chart here, so article 1. And we're going to, it's a short circuit, right? The most common.
Yes.
So this stub that we're going to attach in parallel right here, it's going to look like this. It's going to have a certain length, and I'll call it L stub. It still has the same characteristic impedance Z naught, right? And we have to make sure that at this point, it's going to have a value of minus J2. Do you all follow the trick here? Right? It's admittance. So, come over here. This is Z naught. Now follow me. What is the impedance of the load? If it's a short.
0.
0. What is, take that and normalize it. What do you get?
0.
All right, now take 1 over that. Now you got the normalized admittance. What do you get?
Infinity.
Infinity, correct class? Infinity. Where is infinity?
The right side.
It is right here. This is the point. If it's a short circuit, this is, and we're talking about admittances, that's where you come.
That's why you do the 1 over because we're doing admittance. Or
Yes,
okay.
yes, everything we're going to be doing here, because it's a shunt in parallel.
Okay.
Admittances add like, they add like resistors in series, admittances add in parallel. That's the reason we're doing it. Okay, so that's infinity. Where do we need to go? This is J2, we need to go to minus J2. Can you all hear me? Where's that? I'm going to guess if this is minus J1, it's about here. This is going to be minus J2. And there are no negatives there. Everything in the southern hemisphere that's reactants down here, they're all negative values. And the upper part's all positive, J. With me, class? All right. Now, take your straight edge and draw a line right through there. And tell me what you get wavelengths towards generator.
Wavelengths towards generator.
The outer edge. Say?
Got about 3.323.
0.323. Anybody else?
Yeah, that's what the.
I don't know what Whitmer's book says, but take a look at your own. Y'all get that? Now, here's where you started, right here. This is exactly 0.25 lambda, all right? Here's where you ended up. So the distance that the stub is right here, L or D stub is what? 0.32, is it 325?
323.
0.323 minus 0.25 lambda, what is that?
0.074 valve.
Wait. 0.073.
Yeah.
73. And again, it's less than a tenth of a wavelength, but we're not going to write them nasty letters. Anyway. And of course, we could add another half wavelength, as you said, and you're absolutely right. And then it would be fine. But we're trying to, I think he's trying to give you an idea of how you want to minimize space. Because a lot of stuff that you fabricate, when you have these boards that are VLSI boards and stuff, and they're very small, then you need a small footprint on them. Basically, you don't want to use a lot of space. You want to use the smallest lines possible for any kind of stub matching. You want to minimize the amount of that board. You all know what I'm talking about when I say board? PCB board, Doroid board, stuff like that. That's basically stuff that's etched on copper on the top, and you have to minimize those lengths to do a good job. Okay, now I have that. That's this distance right here. And does that agree with this book?
Yeah. It's 0.074.
Yeah, it's very close.
Yeah.
All right, but that's how you do it. Now, that is with, hear me now, that's with a stub that is a short circuit, right? Let's do the same exact problem, but with an open circuit, all right? Y'all hear me? Now, there's only one thing that changes. We're gonna stop it. We're going from here to here. We're gonna stop at that point. We want the shortest, we're going at the shortest point of attachment. We want the line, the through line to be a minimum. Most of the time they want the stub to be a minimum, and I'm gonna go from here to here, okay? So now I need to still get a minus J2, but this time the stub is gonna be open circuit. Y'all hear me? Okay, so if it's open circuit, let's do the same thing. You're going to see this, and it's going to click. All right, so what is the impedance of an open circuit? Class?
Infinite.
Infinite. What is the normalized value?
Infinite.
And what is the admittance?
1 or 0.
It's 0. So YL, or Y of the load of this open circuit stub is 0. Everybody with me? I bet you see what's going on. So now for the stub length, if it was open, I would come in right here. Isn't this 0 class?
Yeah.
Take your time. Yep, yes. You everybody see this? How far do you have to move? From here to here,
Yeah.
right?
323.
Exactly a quarter wavelength further, or it's just 0.323 lambda. Do y'all see that, class? So this would be, if it's open, I don't know if you put it in there, the stub would be equal to 0.323 lambda. And it would attach just like this, only it would be open. Everybody? Now, any other thing that you want to do, that you can do 2 or 3 things. Either you want to minimize this length that I just talked about. So if you want to minimize this length in the admittance domain, you want to go the shortest distance to this point or this point. You all with me? Now, if your load happens to be here, then it would make sense to move to here. But if your load's out here, it would make sense to move to this point if you want the line, this distance from here to here to be minimum. Y'all hear me? If you want the stub distance to be minimum, think about this. If it's a short circuit stub, impedance is 0, admittance is infinite, right? So for a short circuit stub, you're coming in right here. Just listen to me. Y'all agree with that? That would be where you'd come in. You'll notice that all the values you run into are negative right after that, right? So you would want to make sure your normalized impedance point, either here or here, would have a plus J something. So this would be the shortest distance. Does that make sense to everybody? All right? With me? You follow me on this? Okay. And you? All right. So we're going to do some problems. By the way, make sure you do plenty of these problems, because there's, you know how the last quiz, it wasn't hard. There was a couple of things you didn't really, I guess you didn't consider very deeply, because it was a very easy quiz. We actually did that kind of a problem on the board. It's reverse engineering. It starting at the end. We started at the, actually the input to the transmission line. Here, best way to do this is with problems. So let's go in the back of the book.
We're on 111.
Thank you. All right, let's do 2.38. So let me erase this. Oh boy. I didn't give you 2 by chance, did
You did.
I? I did?
Yeah, that might be his.
I bet you it is. Is this you?
Oh, yeah.
My bad.
I didn't notice it. Just.
Sorry. Oh, this morning I went to class. I felt a little lightheaded, and I'm not sure why. Just one of them days.
Just leave it there. Okay.
These desks are so small. You already
Yeah, I know, right?
I don't know how football players spit in them. Maybe we don't have football players. Just tell you a quick. When I was at Penn State, I had to take economics. And there was, it's a big, economics was big classes, 300-400 people. They had desks similar to that, even smaller. And they were not movable. They were fixed in place. So Matt Suey came in. Matt Suey was a fullback. He played for the Chicago Bears for a bit, 10 or 12 years. He came in trying to fit in the seat. Now, football players in general are large in every dimension. This guy's trying to fit in there. Right about here is where your chest/sternum is. Yeah. Literally, it was the most, like, is a shoehorning, somebody into a position they shouldn't be to begin with. He had no choice. It was, I think they figured out a solution. Okay, so this is 238, right? So give me this.
A load impedance equal to 200 plus J160 ohms
J160.
is to be matched to a 100 ohm line using a shorted shunt stub tuner.
All right, what they want is this. We have to figure out this distance. We'll give me this D, and they call it the through line. I'm just going to THRU, even though it's spelled wrong. And from here, then they want, is it shunt or is it shorted or open?
It's shorted.
All right, now we need this distance here, and this is going to be, I think he calls it D stub. I usually call it L stub, but it means the same thing. And it's going to have the same characteristic impedance, okay? With me, guys? Now, here's the deal on this one. He says that he wants this stub length to be a minimum.
Yeah.
So he wants the stub to be as short as possible. Got me? Did you have a question?
I have a question. So it doesn't say whether to use it like in series or parallel.
Say shunt, doesn't it?
Yeah.
Oh, does shunt mean parallel?
Shunt means parallel.
Okay. Gotcha.
And it's just one of those terms that's used by in industry all the time. Okay?
Is there a term for series? Or
Series.
It's just series. Okay.
They'll say series.
Gotcha. Okay, cool.
All right. And if you have any question about anything I ever give you, on a quiz, test, or anything, just ask me. I'll tell you what, if it's shunt or series. Okay? So, for this one, let's go ahead and do it. Let me draw my Smith chart. Get one out. If I was you, I'd get a new one. And for starters, we're going to I always start this way. Find the normalized impedance. That's equal to what? 200 plus J160 over 100. So it's just going to be what? 2 plus J1.6. That's the first thing. We'll plot that point in a second. But what do I really need? Because it's a shunt in parallel. Admittance. So really what we need is YL, which is 1 over ZL. And can you give me that? It's going to have a negative J.
0.305 minus J.244.
244?
Yes.
Your calculator should do this in an instant.
That's what I did.
Now, you can also do it this way, and I do it this way all the time. 2 plus J6, let's see, 2 is about here. Take a look at your Smith charts. That's about R equal 2. And 1.6, well, this is J1. 1.6 is about here. So you're going to have to look. So you see where these 2 points meet. And this is going to be ZL, which is 2 plus J1.6. Then you can take, y'all with me? Take your compass and then draw a circle around here. About like that, right? That's constant reflection coefficient. Then take your straight edge and go right from this point through the center outward, and you're going to find this is going to be YL, which is 0.305 minus J 224. 0.224. Y'all agree with that? Just looking at your Auburn youth programs. Is that part of Camp War Eagle stuff?
No, I'm just setting up stuff for junior high and like hospitals.
You know, this is summer and all the camps are here. Basketball camp will be here in no time. They're going to have Camp War Eagle, they have cheerleader camp, they have, I don't know how much.
Our housing work, things like dance, swim, equestrian.
Yeah, well, the basketball one with Bruce Pearl gets jammed. I go over there and jog and stuff like this over in the Coliseum. I mean, over in the rec center, and it's a madhouse over there.
They
Sometimes.
invite like a ton of high schools to it. I did it in high school. It was insane. A ton of high schools.
But they have some of the real players out there too
Yeah.
playing with me. I see these guys, you know, a guy at like 7 foot. Well, when you see Walter Kessler, it's not a high school kid.
Yeah.
All right. So, y'all with me on this? Now, what's the next thing I need? Think about it.
You need your
How about
wavelengths
this
towards
mile
generator.
marker? There's no specific order. Give me the wavelengths towards generator mile marker here for YL. Y'all, are you with me on this? How to do it?
Yeah.
I
Go
got
ahead.
about
What?
I got about 0.459, but I don't know if that's right.
0.45? Well,
I
this
got
is 0.5. That's about right.
458.
458.
0.458. Land somewhere around there.
Yeah.
Yes, and again, good Smith charts give you an added benefit. With me? All right. Now, this is the key important point. If I move from here I'm going to move to either the point right here, which is going to be 1 plus j something, or the point here, which is 1 minus j something. Y'all with me? All right, what's that 1 plus j? Tell me what that is about.
Well, I got about 1.4.
This way. About 1.4? We'll go with 1.4. What do you get down here? 1 minus j 1.4. It's got to be the conjugate if you did it right.
I got like 1.35, but it's close enough.
What did you get?
I got about the same thing, so.
What does the book say?
Unless
you have to, unless you know.
It's an example.
I mean, the solutions are up though. You can check.
On OneNote.
They should be.
Okay.
I put them up there, I promise you. I mean, I assume they're still there. I had a student take something down one time. By accident, I gave him the ability to edit it. He didn't mean to, but it happened. All right, it's about that. Do you agree with that, class?
Yeah.
Okay. Now, so 1 plus j 1.4. Now, here's where everybody pays attention. Got to pay attention. We're in the admittance domain. We have a short now. I'm going to draw it over here. I have a short circuit. We're going to assume same characteristic impedance. We look at this. ZL for a short is
0.
0. Normalized is still 0. YL for a short is infinite. Do you all agree? Now, think about where you come in. Where is the infinity point?
To the very right.
Right here. So we're coming in here. You all hear me? If we just move a little bit this way, it's negative very large value, right? Minus j something. You all see that? Just look there. Can you see it back there? All right. And they said they want this line minimized, right? So that means we want this to have a minus j value that would match it. Does this make sense to everybody?
Is it because that's closer to the that's closer going this way to the point?
Well, hold it. I didn't talk anything about this distance. I'm talking about the distance on the, from this point on the actual matching stub, right? As we just start, it's negative j, right? So it means we want to match and hit a point where it's positive j. Y'all follow me? That way, it'll be the minimal distance over there. Can you follow me?
Yeah. It's because we're going this way over like.
We're going this way,
Yes,
right?
yes. And so.
Here's YL.
And so a negative would be closer to the positive because we go through the negative side.
Well, we
first.
want the minimum. This is the minimum distance,
Yeah.
right? We don't care about the length, the distance from the load, just
Yeah.
the stub length.
Yeah, I know.
All right. The stub length starts negative just as you move an inch, so we have to match it to a positive j value for the load's intersecting point. 1 plus j something. You all with me? Now, just watch. This will make sense. So we're going to go to this point right here. Right here. My bad. So take your straight edge, drop right through here, and give me wavelengths towards generator there. Remember, admittance to
You got 0.172.
Yeah.
0.172 lambda, and you can look at Whitworth's solutions if you want. Now, how far do we actually move on this line? Well, we're going to go 0.172, and it's going to be what? Minus where we started from, which is 0.458, right? And what do we have to do?
Add a halfway.
Right, add 0.5, so what's that?
2.214.
0.214 lambda. That's how far we have to move from the load before we attach. The value right here at this point, if we didn't attach anything, is going to be what? It's 1 plus j, what is that, 1.4? Yeah. About, right? About that. Now, we got to get rid of that 1.4. We got to add a negative minus j 1.4 to it, right? It's an admittance that's going to be in parallel. So we come over here. Here's where I am. I start here at the load, and I move until I hit, it's about here, minus J 1.4 on the outer 1.4. Can you all see that there? Can you see it? Class? I'm looking at this, your shirt, I'd love to be fishing.
I don't know about me.
Yeah, I love it. I mean, I wanted to get down there. Didn't get down there yet this year. To golf. I love Fort Morgan and inshore fishing. Okay, now, you all see that?
Mm-hmm.
What's the mile marker out here?
0.348 lambda.
0.348 lambda. We've had this one, didn't we? Didn't we have that mile marker before? All right, so take that, and what do we subtract from it to get the length of the stub? This is 0.25 lambda, right? Can you all follow me? Oh, you want to talk to my class, right?
Yes, whenever you're done.
Give me 1 second. So this distance from here to here is what? 0.3?
Is it 0.348 minus 0.25?
Right, what is it?
Yeah.
0.098.
About at that hairy edge. Fine. Do you agree, class? So that means, huh?
You left off the zero.
What?
You left off the zero.
Zero.
0.098.
Oh, I'm sorry. Yeah. 0.098 lambda. That's the length of this stub.
That's that is okay.
0.098 lambda. It's just about a quarter weight, or a tenth of a weight. So we're just about the hairy edge of yes. We can do it. But you all follow me in this?
Yeah.
Now, remember, the reason we moved to this point because we wanted that plus J. What happens if it's an open circuit? Class?
We go to the minus.
Probably the minus, right? You all follow me? Or, I mean, actually, tell you what. She wants to talk. I'll see if I have time. Come on up, miss. Introduce yourself. Tell us why you're here.
So my name is Tiffany. I am a graduate assistant for the Engineering Tutoring Center.